So today, what we shall first look at scattering of two particles. So far, we have been looking at single particle scattering due to the 5-4 theory, 5-4 interaction that we have introduced. But today, we shall look at the scattering of two particles. And you can imagine what kind of a diagram you can get in the scattering of two particles. So it is very simple. So the two particles come like this. So this has momentum P1, this has momentum P2, and since this is a 5-4 interaction, therefore you should get something like this, right? So this is the interaction vertex. There are 4 lines at this point. So this is the this will be one of the terms that will contribute to the scattering amplitude, and this will be the leading term that will contribute to the non-trivially to the scattering amplitude of two particles. So suppose let us start from two particles. What we need to calculate, or what we want to calculate, is the following. We want to calculate this, right? So in the in state, we have two particles, and the out state also contains two particles. And this, as you know, that this in state and out state, these are basically the time independent eigenstates of the full theory, fully interacting theory. And now you can write it down in terms of the S matrix. In terms of the S matrix, it will be written in this form. And now you know what the form of this S matrix is. Let's put it there. So this is the time ordered product. If we work in natural units, so h bar is equal to 1. So have so this is what we have, and let me write down the Lagrangian density of the theory. This is the theory that we have, and this is all these fields are in the interaction picture, so they evolve by the p Hamiltonian, and from here you can immediately see that the interaction part of, so this is the Lagrangian density. So if you make the Legendre transform, you will get the Hamiltonian density and write these in terms of pi's, but this term will remain the same, but it will just, the sign will switch, so it will become a plus sign. So from there, we can immediately read of what VI is. It is basically dqx of lambda by 4 factorial by 4. And therefore, when we integrate it over dt, so this becomes d4x, and this becomes lambda 4 factorial. So this is the scattering amplitude for the scattering of two particles. And now you can see, you can expand this. If you expand this, then you will get Q1, Q. First term is identity. Second term is, so what I do is you can write this in this form, 4x. Keep the time ordering outside, 5-4 x, then plus minus I lambda square by 2 factorial whole square for x, for y, for x, y, plus so on, then we have so this is the scattering of two particles that we look at now. And from here you can see that this first term, this is a trivial term. So here it just basically means so this first term is the following Q1, Q2, P1, P2, and these are basically eigenstates of the P part of the Hamiltonian. There are no interactions here, so they are just eigenstates of the P part H0, and therefore you can write this in the following way because of the three vacuum AQ1, AQ2, A dagger, P1, A dagger, P2, this. And you can now contract these things, and what you have to do is the trick is to evaluate this vacuum expectation value is to take all the creation operators to the left and all the annihilation operators to the right so that it kills the vacuum. And if you do that, you can do it easily by using these commutators. So from here what you will get is you will get these lines like this. So a particle comes in with momentum P1 and goes out with momentum P1. So let me just write P1, P1. Similarly, a particle comes in with momentum P2, goes with momentum Q2, and you can have also a particle coming in with momentum P1, going out with momentum Q2, and particle coming in with momentum P2 and going out with momentum Q1. So these are trivial. So these processes do not take into account the effect of interactions at all. They do not see the interaction. So this is a trivial term that you get. But the interesting term starts from here. This is the first interesting term that you get. Let us go to the other side of the board. So if we look at this term, then what we shall have is the following. We have Q1, Q2, then we have time order product of minus I lambda by 4 factorial. Then we have d4x by 4x. So we just look at the first order term now. So you can write this as A1. So this was A0. So we write this as A1. And then we have P1, P2. And once again you can write this as time order product of okay. So this you can do the following thing minus I lambda by 4 factorial vacuum. And also put the integral outside d4x. Then we have a q1, a q2, with the time order product. Q1, Q2, then 5 4 takes, then a dagger, P1, P dagger, 2. Okay. So this is the term, and this is the expression that we get for A1. And you know by now you know how to evaluate this. So you have to evaluate this by using Wick's theorem. And one of the terms that you will get here, you can see already that you get something. So you have 4, 6, 8 operators. We just write this in this way. This is the time ordered product. There is a time ordering here. Therefore, you will get contractions and there will be contractions of this form, this with this, and this contracting with this, and this contracting with this. Okay? So that will not give rise to an interesting process. The interesting process will come out from here. If you contract this with this, this with this, this with this, and this with this. So there are 4 phi's. You contract each of the phi's with the A's and A daggers. That will give you the interesting process, and you know what it will come out to be. It will basically give rise. So you can see the full board now. The contractions that I have drawn there, it will basically give rise to this vertex. This is the thing. This particular way of contracting will actually give rise to this vertex. And this will be the first non-trivial contribution to the scattering amplitude. So this is the basic vertex that you get for the scattering of 2 particles using the 5-foot theory interaction. Scalar field with 5-foot interaction. Let us now look at the scattering amplitude at the second order. So let us look at this term. Look at this term. So what can this term give us? So without even now, since you have some experience with 5-foot theory and the Feynman rules of 5-foot theory, and also how to write the Feynman diagrams, you can immediately tell what will be the second order correction to this scattering amplitude, amplitude A1. You can immediately tell us. So it should be something like this: 2 particles are coming in. At second order, there will be 2 vertices, right? So if the particle comes with momentum P1, this particle comes with momentum P2. There are 2 vertices. This particle goes out with momentum Q1. This particle goes out with momentum. So you can see this should be the correction, or this should be the correct Feynman diagram corresponding to second order in the perturbation series expansion, in the S matrix expansion. And you can see that this looks like a fish. So this is called a fish diagram. This Feynman diagram is called a fish Feynman diagram. So this diagram will contribute with the correction term to the scattering amplitude is A1. You can immediately see how this diagram can arise by performing the Weeks expansion, by using the Weeks theorem here. This is very simple to do because there are 8 operators, 8 phi operators, and 2 annihilation operators and 2 creation operators. So you can see that it will be something like this: A Q1, A Q2, phi x, phi x, phi x, phi x. Then you will have phi y, phi y, phi y, phi y. So 4 phi y's, and then you will have a dagger P1, a dagger, and then the right. And it is obviously time ordered. Now you can immediately see how you can get such a diagram. The way to see that is the following. You can see that there are 2 propagators. So 2 of the phi's, so 1 phi x and phi y should contract with each other. So there should be a contraction of 1 phi x with 1 phi y. So that will give you this internal propagator from this vertex to this vertex. There are 2 such propagators or internal lines. So another phi x should contract with another phi y. So that gets rid of 4 of the phi's. So there are 4 phi's, and it is very easy to see. Now you just contract this phi with this A with this phi. So again 2 phi's are gone. And contract this phi with this A dagger, this phi with this A dagger. Right? And now all the phi's are gone, all the A's are gone. So you will get a non-trivial vacuum expectation value, and this will correspond to this diagram. And what we shall do now, you can actually calculate this explicitly. You can try to calculate this explicitly and work out the scattering amplitude at the order lambda square. But what we shall do now, to have some experience with Feynman diagrams and Feynman rules, we shall try to calculate this diagram using the position space, or write down the expression for this Feynman diagram using the position space Feynman rules. You can actually immediately write down the expression for this diagram using the momentum space Feynman rules. That you can do immediately. But let us have some practice. Let us write the expression for this diagram in the position space. So let us do it now. Is this clear? Are you okay with this part?
Yes, sir.
Let me rub this portion out. I would urge you to do all these calculations once more at home. So that will make you familiar to work with Feynman rules and Feynman diagrams. So our aim is to calculate this diagram. This is momentum P1, momentum P2, P1. We want to calculate this. So this has 2 vertices, 4 external lines, and 2 internal lines or propagators, and 1 loop. So let us write down the anatomy of this diagram. So external lines, number of external lines is 4. External lines are denoted by capital E. So number of external lines is 4. Number of internal lines, I, is 2. Number of vertices is 2. And number of loops is 1. So this actually characterizes this diagram completely. So these are the numbers. So let us keep this in the background. These numbers will be important later. You will see why they are important. Okay. Now let us try to write down the expression for this diagram. So as you know, there are 2 vertices. Let me call this vertex as Y, and let me call this vertex as W. So you know that for each vertex there is a factor of minus I lambda. So that will give us minus I lambda whole square by, you have to divide this by the symmetry factor, which arises from the number of ways, in which this particular diagram can arise out of contractions when you use the Wick's theorem. And that number, you can see that there are 2 propagators which are joining these 2 vertices. So the symmetry factor for this diagram is 2 factorial, which is 2, which will divide by 2. And for each vertex, you have a factor of minus I lambda, and then you have to integrate over the vertices, over the position coordinates of the vertices. So there will be integrations over D4y and D4w. So that takes care completely of the symmetry factor and the vertices. Now let us come to so vertices are taken care of, symmetry factor is also taken care of. Now let us come to the external lines. So for each external line, you will have a factor of np1, which is that normalization factor that you already know, np1 e to the power of minus I p1 dot y, since I called this vertex as y. Then you will have in p2 e to the power of minus I p2 dot y, since this momentum is p2. So these 2 external lines are taken care of. Now let us look at these 2 external legs. These are also sometimes called external legs or lines. Now we have nq1 e to the power of I Q1 dot W in Q2 to the power of I Q2 dot W. So the four external lines or external legs are also taken care of. Now you have to concentrate on the propagators. So for P, there are two propagators. For each propagator, you have a factor of I delta F y minus W. So that gives us I delta F y minus W and another I delta F y. So this is the full mathematical expression corresponding to this fish diagram. This fish diagram is actually the correction term at the second order to the scattering amplitude. Okay, so this is the diagram that you will get if you expand the S matrix to second order. So this is the full expression corresponding to this thing. You can immediately write down the corresponding expression in momentum space also. It is very simple to write. So let us do it. So this is the expression in momentum space. What is the expression? This is the expression in position space. And what is the expression in momentum space? This is not working. The other side of the board. Can you see the board?
No, sir.
You cannot see the board.
Full board is visible, sir.
Board 1. Yeah, now it is visible, sir.
It is visible?
Yes, sir.
Okay. But somehow this remote is not working because I cannot zoom this part of the board and the other side of the board, but you can see the full board probably, right? So let's see. So we can see that this is the expression. You have applied the Feynman rules in position space, and this is the expression which corresponds to this diagram, this fish diagram. But let us write down the corresponding. Let us now use the Feynman rules in momentum space and write down the corresponding expression in momentum space corresponding to this diagram. So what will be this one? So this is once again Q1 and Q2 and Q1 and Q2. And what will be the expression for this diagram in momentum space? The momentum space Feynman rules are the following: for each vertex, you have a factor of minus I lambda. So there are two vertices. So it's whole square. The symmetry factor of the diagram is 2. So you divide by 2. And for the external legs, you just put in the factors of n, p1, n, p2, n, p1, n, p2. So this takes care of the external legs, and there is in the momentum space, for the momentum space Feynman rule, there is another rule that the overall 4 momentum conservation must be there, and for that we have a factor of 2 pi whole to the power of 4 delta function, 4-dimensional delta function. What is the overall momentum conservation? 4 momentum conservation. P1 plus P2 must be equal to Q1 plus Q2. So we will have P1 plus P2 minus Q1 minus Q2. So this is the overall 4 momentum conservation. So everything is taken care of except these two propagators, the loop. So here let us think in terms of loop. For each loop, there is only one loop here. For each loop, you will have a loop integral. How many loops are there? The number of loops is 1. So there will be only one loop momentum because there is one loop. So there is only one independent momentum. Why? Because you can see that if I call this momentum K, then this momentum you can call anything. You can call R. You can call this momentum as R, but R will be nothing but P1 plus P2 minus K. So R is determined in terms of the external momentum of the particles, and the loop momentum k. So the other momentum is not independent, it is dependent. So the rule is that the number of loops corresponds to the number of independent moment. So one loop means one independent momentum k. So there is one loop integral d4k divided by 2 pi whole to the power 4, and then you will have, now you have to take into account the propagators. So let us come back to this diagram. So one propagator is this. So this will give us the factor of I divided by k square minus m square plus I epsilon multiplied by I divided by this propagator. The momentum is basically P1 plus P2 minus k. Therefore, we will have P1 plus P2 minus k whole square minus m square plus I epsilon. So this is the full expression in the momentum space. Is this clear?
Yes, sir.
So is this clear? So what we have done, we have taken the fish diagram, and we have also seen how this fish diagram can arise, and we have evaluated, we have written down the mathematical expression corresponding to this fish diagram in position space. We have also, by using the position space Feynman rules, we have also written down the mathematical expression corresponding to the fish diagram in momentum space. You see, there are no position variables involved here. All the vertices y and w, they are integrated out, because in position space there were integrals over the vertices d4y and d4w. So they are integrated out. There is no y and w here. Only momentum things are, only the momentum variables are there. There is one loop integral over the loop momentum k. The external factors are there corresponding to the external legs. The vertices factor is there. The symmetry factor is there. The overall momentum conservation, core momentum conservation is there, and the propagators corresponding the internal lines, which are the propagators, the expressions for those are also there. So this is the expression. This particular thing is the expression corresponding to this diagram in momentum space, and we have used the momentum space Feynman rules here directly. Now I shall show you one more thing, just to give us some practice. I shall convince you that indeed this is the correct expression that we have obtained using the Feynman rules in momentum space. What we shall do is, we shall take this expression that we have written down in position space and Fourier transform it, and show that the Fourier transform of this expression gives you this expression, gives you the expression on the other side of the course. We shall do that calculation now, to convince you that indeed the Feynman rules corresponding to the Feynman diagrams indeed work. So this is basically. This is the expression that we have. So let us do it here. Minus I lambda whole square by 2 d4y w. We have obviously these factors in P1 and all that. So we shall write these factors in P1 into n P2 into n Q1 into n Q2 as this thing. We shall write this as. So this particular thing that I've just drawn here, this is not a Feynman diagram, by the way. So this stands for in P1 in. I'm just introducing this notation so that I don't have to write it over and over again. So this stands for this product. So we have d4y, d4w. Then we have e to the power of minus I p1 plus p2 dot y times e to the power of minus I from this q1 plus q2, this plus I, q1 plus q2 dot w And then we have the propagators. And what we shall now do is Fourier transform the propagators. So we have two propagators, delta I delta F and delta this one. So we shall now write the Fourier transforms of these. This is d4 k1 by 2 pi over to the power of 4 I divided by k1 square n square by epsilon multiplied by d4 k2 Is this clear? What we have done is we have just Fourier transformed this expression. We have just written everything in terms of the momentum case. Let me now log this part out so that I get some space to do the calculation. So let us now take this expression and perform the y and w integrals. So this is equal to minus I lambda square by 2. Then we have this object, which stands for the product that I have written down on top. And then we have d4 k1 by 4, the momentum integrals I. So let me just write for the time being, let me just write it down in the following way. I delta F K1. So this actually means delta F K1 basically means 1 divided by this factor K1 square minus n square plus I epsilon. And then we have into I.
Sir.
Yes.
Sir, so
I think you have missed an exponential factor while writing the Feynman propagators. I mean, that is the form for I delta F0. You have to include exponential of I y
Correct.
minus.
Yes, I missed this factor. Thank you very much. So this will be I. You are absolutely correct. I missed this factor. E to the power of I. Thank you. Thank you very much. So I missed these exponential factors while writing the Feynman propagators. Now is it correct?
Yeah,
Now
I
is it
think
okay?
so. Yeah.
yes,
Okay. Good. You are absolutely correct. So let me just write it down over here. I delta F, this thing is basically integral G4K by 2 pi whole 4 I delta F K, where delta F K stands for this factor 1 divided by K square minus n square plus I epsilon, and then we have e power of I K Y. So I've written that on top. This is the factor, exponential factor that I missed while writing it on the board. So now I think everything is correct. So we have this thing, I delta Fk2. Let me also write what delta Fk is. Delta Fk basically stands for 1 divided by K square and Z square I epsilon. Okay. So this is what we have. Now this times the integral over d4y. So integral over d4y will give me what? Let us now look at only these terms, the y terms. This will give us I p1 plus p2. So that takes care of this term, and you have to search where are the other y's. So this here there is one y, and here there is another y. So what we have is minus k1 minus k2 dot y times integral d4w to the power of. Now you have to write down the w integrals. So w integral will be I q1 plus q2. So this takes care of this term, and then this is the w integral and this is the w term. So we will have minus k1 minus k2 once more. Now you can see that you can easily perform this y and w integrals. These are basically the 4-dimensional delta functions, and therefore you will get a 2 pi whole to the power of 4 from here and 2 pi whole to the power of 4 from here. And so let me just write it down now. So this gives us a factor of 2 pi whole to the power of 4 delta 4 q1 plus q2 minus k1 minus k2. And this also gives us a factor of 2 pi over 4-dimensional Dirac delta function t1 plus t2 minus k1 minus k2. So now you can see that the y and w's are gone. We have performed the y and w integrals, the spatial integrals, and now you can impose this Dirac delta function. See, q1 and k2 is therefore equal to q1 plus q2. Therefore, you can in this q1 and k2, you can replace this by q1 and q2 minus q1 minus q2. So you can now see that this actually, we have got this term, overall momentum conservation. That is now there. We have minus I lambda whole square by 2. This factor is basically the product of those normalization factors, which are basically these. We also have this overall momentum conservation. So everything is almost there. So now what we have to do is the following. We have to perform this delta function integral. And that's it. So immediately we can see that 1 2 pi whole to the power of 4 cancels with 1 2 pi whole to the power of 4. And therefore this will give us this is therefore equal to minus I lambda whole square by 2. We have this factor. Then we have this factor 2 pi in the overall momentum conservation. P1 P2 minus Q1 minus Q2. So this is now we have the two integrals which are d4 k1 by 2 pi whole to the power of 4, and the other integral is over d4 k2, but now you don't have a 2 pi whole to the power of 4 because that factor has cancelled away. Now I have been able to zoom it. You can now see this thing. And then we have I delta F A1 times I delta F K2 times the Dirac delta function delta 4 Q1. So what we could have done is the following. We could have also kept this intact. We could have kept this as P1 and this doesn't matter. And here we could have written as P1. It's the same thing because delta x minus y is delta y minus x. So you have this thing, and this term we can write it down as P1 plus P2 minus K1 minus K2. Now we can perform any of one of these integrals K1 or K2. Suppose I perform the K2 integral. So if you perform the K2 integral, then this is gone. The integral over K2 is gone. So what we have is the following: I divided by K1 squared minus M squared plus I epsilon, which was delta F K1. And in this delta F K2, you just replace K2 by P1 plus P2 minus K1 whole square minus M square plus I epsilon. Just replace it. So you'll get this. And now, since K1 is a dummy variable, so you can replace K1 by K everywhere. And you can now easily see that the expression that I wrote down for the fish diagram in the momentum space by using the momentum space Feynman rules, we have actually derived it from the expression in position space by Fourier transforming. This exactly corresponds to the expression that is written down directly without calculating anything. I just applied the Feynman rules in momentum space. Here I didn't calculate. I didn't need to calculate anything. I just wrote it down, wrote the mathematical expression here directly, and I've shown you that if you Fourier transform the expression in position space and do the calculation, you will get that expression that I wrote down earlier. Is this clear?
Yes, sir.
So today, what we have shown, we have seen in today's lecture so far, is we have seen the we have looked at the scattering of two particles, and we have looked at what is the interaction vertex in such a case. The scattering of two particles, that is the first leading term that you will get in the scattering amplitude, and then we have once again started to calculate corrections to this scattering amplitude. And the first correction comes at the second order in perturbation theory. So this is the correction term that you will get. But once again, you can see from this expression, see this integral over the momentum k is there because you have a loop. This is a loop integral. This is a loop. So there is a loop momentum. There is a loop momentum that is flowing inside the loop, right? And therefore, you have an integral over that loop momentum. But now, once again, you count the powers of k. How many powers of k are there in the numerator? There are 4 powers of k in the numerator. And how many powers of k are there in the denominator? 2 powers of k, and from here there are 2 powers of k. So there are 4 powers of k in the denominator also. Okay? So 4 powers of k in the numerator, 4 powers of k in the denominator. So this particular integral is also divergent, and it is logarithmically divergent. So this has a log divergence at large scale. Log divergence at large scale. In the other lecture, the previous lecture, we have seen that we had this diagram. So P comes here and Q goes from here. There is a loop momentum field that is flowing inside the loop. And this diagram was quadratically divergent at large scale. So at large scale means this is a UV divergence. This is said to be an ultraviolet divergence. Large momentum means small wavelength. So it is a UV divergence, ultraviolet divergence. So this diagram had a quadratically, this was quadratically divergent in the UV limit at large scale. But this diagram is not quadratically divergent, but it is also divergent. But it is divergent in a logarithmic way. So this is called a log divergent diagram. So once again, as I mentioned to you in the previous lecture is that we are doing perturbation theory, and since this is perturbation theory, therefore we are calculating corrections to the scattering amplitude to the leading term. Yes. And you can go on in perturbation theory. You can go on, calculate a third order, fourth order, and see what happens. So you get correction terms. And why is this called perturbation theory? Because it is perturbation theory is valid when the correction terms that you calculate are indeed smaller than the leading term, the expression that you or in the physical object that you want to calculate. But here you see that all these corrections are themselves blowing up. They are not small terms; they're infinities. And therefore, it seems that whatever quantum field theory, whatever theories, the theory that we are doing and we are trying to quantize, and from that quantum theory, we are trying to calculate things which are experimentally observable, like scattering cross-section and things like that. These things will diverge. Because it seems that perturbation theory is failing because this correction term is not small. This is very large. And it's not only large, this is infinite at large scale, at large momentum. So it seems that something must be wrong here. There are infinities in quantum field theory. At the start of the course, I told you that the vacuum has an infinite amount of energy, right? Infinite amount of zero-point energy. And this infinite amount of zero-point energy arose because due to the Heisenberg uncertainty principle, right? Because the zero-point energy actually arises in the harmonic oscillator. You encounter the zero-point energy first when you look at the one-dimensional quantum harmonic oscillator, and there you see that there is a zero-point energy, and that zero-point energy owes its origin to the Heisenberg uncertainty principle. And similarly, in quantum field theory, a quantum field is basically an infinite bunch of collection of free oscillators. A free quantum field is an infinite bunch of quantum harmonic oscillators. Each harmonic oscillator contributes a zero-point energy, and therefore, infinite number of oscillators will contribute infinite amount of zero-point energy. And therefore, the vacuum has an infinite amount of zero-point energy. So already we have encountered a divergence in quantum field theory, and that is in the free quantum field theory itself. The divergence was there in the free QFT. But now we have started to look at, but there in the free quantum field theory, we said, okay, we can get rid of that divergence in some way. We can normal order. We can say, okay, that infinite amount of energy, I just throw it off, and that is my zero of energy, and from there I measure my energy. So you can do some, you can say some things such as normal ordering. You can get rid of that. But it is also important that that particular infinite amount of zero-point energy that the vacuum has in quantum field theory has real physical effects. It is not that it's just unphysical and you can just throw it away or it creates a problem. It indeed has a physical effect. But now we have started to look at interactions, and we have started to look at we are trying to do perturbation theory by assuming that the coupling constants in the interactions are small, and therefore we are doing perturbation theory just as we do in quantum mechanics. And we start calculating corrections, and when we start calculating corrections, we encounter infinities once again. And this is the problem. This is a real problem with quantum theory, and we have to understand how to overcome this problem in quantum field theory. Okay. So this is the thing which I want. Yes.
Actually, I have a confusion.
Please go.
I mean, the loops in the Feynman diagrams, we cannot apply any time direction to the loops because those are Feynman propagators. So how can we actually physically interpret these loops? I mean, I am not completely understanding what these loops mean.
These things that you have, these loops, here
Yes. What is the physical process behind that loop? I mean, we cannot apply any time direction to the loop.
No, you can apply. This is the direction of time in this diagram.
But sir,
this is the direction of time. See, all these diagrams have arise from where you have perfectly time ordered your S matrix. The S matrix is time ordered. So when a particle, so let me draw the diagram once again. You have two particles coming in, right?
Yes.
Two particles coming in. It interacts at this point. Then it goes like this. So at each vertex there must be 4 lines because it is a 5-node theory. Now it goes up means you are going to a later time. The particle propagates to a later time, and then it again meets at this vertex. This vertex and this vertex. This vertex is at a later time than this vertex. So this is the direction. This is the flow of time t, and now it goes away. So these are the external particles. The internal particles, they come in, they interact by some interaction process. They meet at some point and they again go away.
But sir,
The interaction is due to the 5-fold interaction that you have introduced in your theory.
yeah, that is okay. But I mean, when we studied the Feynman propagator, there was a contribution from the advanced Green function and also from the retarded Green function. So I mean, time is coming from both the ways. I mean, we can also think that some future particle is coming.
No.
And
Here, in this case, there is no future particle. See, see, this is a real scalar field theory, right? This is a theory of a real scalar field. So there are no antiparticles here. There is only one species of particles, which are the quanta of the field phi. So there are no antiparticles, and so there is an interpretation that these antiparticles move backward in time. So that is not there. There are no antiparticles in this theory. So this particle this particle and this particle, they are the same mass, they are neutral, they are spin zero. They are electrically neutral, they are spin zero and the same mass. So these are the same particles, same species of particles. They are not one is not the antiparticle of the other. So they are coming here, interacting. So meeting at this vertex, the two vertices are connected by propagators. That is why we calculated the scalar, the real scalar field propagator at the beginning of this course. So these are propagators, and then again they are becoming free. They are going out.
yeah, okay. So,
And you can say that
but the diagram.
Sir,
you can have something like this also. So it meets, again it goes, again it goes. So this particular diagram will contribute to the scattering amplitude at which order?
third order.
At the third, because there are 3 vertices.
Okay,
Sir,
but sir, the diagram you drew the previous day, I mean, for one particle, and there was 3 Feynman propagators connecting W to Y. So how
Yes.
will you explain that process?
Okay, see it is, you look at the interaction as I've been continuously telling to you. The particle is coming, momentum p, so there is a vertex. And the diagram that I talked about, that is at second order in perturbation theory. How can you get a second order diagram? What is the way of getting a second order diagram? At this point, this is the vertex. There must be 3 lines. This is one line, this is the other line, and this is the third line. Because it is a 5-4 interaction.
Yeah,
That
that
is
is
why,
true. But
that is
how
why
will
you
you?
have 4 lines at this vertex.
Yeah, that is true. But in this case, can you tell that the particle is going along the straight line or along the curved line? Can we specify
That is not
any such thing?
important. That is not important whether it is going in a straight line or curved line. That is not important. That is not important here. Why do you want to think about whether this particle is going like this or this? That is not important. You can always
No,
bring
no.
it to a straight
Along
line.
the path that you have drawn, I mean, can it happen that the particle
Okay,
is
I
going
understand.
simultaneously
I
through
understand
if
your
I
question. The idea is you should not take these diagrams in a very serious way. These are just intuitive way of understanding of what is going on. You want to draw pictures. You have an intuitive way of understanding things. Okay, so you have a very complicated interaction and you have a very complicated machinery to calculate everything. The machinery of S matrix, what are in and out states, the interaction picture, the evolution equations, and everything. The machinery, they have a formalism for calculating everything. And then after that, you have, in order, you get an expression, but then also you cannot proceed. You have to bring in the Wick's theorem. To calculate those expressions, you have to apply the Wick's theorem. So the machinery is quite involved. You have a very difficult machinery. And what Feynman did is, once you calculate, it's a very complicated calculation. But now he's able to associate every mathematical expression with some intuitive picture, which will help us to understand. You should not take this very seriously that okay, the particle, why did I draw a straight line from here to here, from here to that point? Why it is not like a weekly, why is it not a curved line? The point of curved line and straight line is not important here. This is an intuitive picture corresponding to that mathematical expression. So you are able to associate. See that mathematical. Is it easier for you to understand or get intuitive ideas or intuitive feeling from those big mathematical expressions? Is it easier for you?
I have got.
Or is it easier to get intuitive feeling from this diagram?
Yeah,
Which
yeah,
one
that's
is
okay.
easier?
Yeah, that is okay.
Will you understand? So it is not that
Yeah.
whether it is moving in a straight line or whether it is moving in a curved line, it is not that thing. These are just intuitive pictures. Obviously, you know in quantum mechanics that trajectories does not make any sense in the first place. These are like trajectories, right? So trajectories do not make any sense. So why are we drawing trajectories? These are just intuitive pictures to understand, yes, okay, this kind of processes are going on. And this picture is actually related to a very complicated mathematical expression. And the idea is that if you can draw all the pictures, I give you a theory, not 5-foot theory, say 5 cube theory, or 5 to the power of 6 theory, or any theory I give you, any interacting theory I give you, and I tell you also, okay, calculate the scattering amplitude of or the scattering cross section of two particles. Two particles are coming in and scattering by this interaction, complicated interaction, and they are going out. Calculate the scattering cross section. If you can identify what are the possible Feynman diagrams for this theory, and if you know the Feynman rules of that theory, then you can immediately draw a diagram, apply the Feynman rules for that interaction, and just get the scattering amplitude immediately. Once you get the scattering amplitude, take the mod square as you do it in quantum mechanics. Take the mod square, it will give you probability. And from there, this is the probability amplitude. Now we will get the probability density by taking the mod square, and then you can proceed to calculate the scattering cross section for that process. And
Okay.
the importance of all this is that you can say, okay, whatever you are doing, how do you know that this is relevant or not? It is relevant because when you calculate by using this complicated, this highly technical formalism, when you calculate things and calculate cross sections, decay rates, you just match them with the experimental values, and they agree completely with each other. So that is the triumph of what you are doing.
So,
Huh.
uh, which one we are calling the UV divergence case?
Oh, this is the UV. This diagram is UV divergent because the divergence is log k, right? It will go as logarithm of k. So when k is very large, k large means lambda is small, wavelength is small. So for large k, log k is divergent. Therefore, this is a UV. This the fact that this is divergent for large k means ultraviolet light divergence. But the The point is, what kind of ultraviolet divergence is it? Is it a quadratically divergent, or is it a quartic divergent, or is it a logarithmic divergent, or is it something else? This is a logarithmically divergent diagram, and all these are UV divergent because these are divergent at large scale, at large momentum in small wavelengths. So at very high energies, these diagrams are divergent. At
Okay,
very
sir.
high energies, large
O-
momentum, large energy, small wavelength. So at very high energies, these corrections are divergent, and that is why we call it to be ultraviolet diagram.
Sir, I have a question about the time ordering of the self interaction diagram actually. P loop K and then Q. Sir, for the loop, it seems that it happens instantaneously. I mean, for the loop trajectory, it is at a fixed time. So that part I am not just understanding.
Which one? This one?
Yes, sir. Only the loop part. There it has to happen at a fixed time.
Yes, yes, absolutely. It happens at a fixed time. But once
Okay.
again, we should not worry about much about this thing because this loop is actually a virtual particle.
Okay. Okay.
These are not really on-shell particles. This k square will not satisfy the dispersion relation. They are off-shell.
Okay.
So don't think about causality or about special tunability. How come this is coming in a loop at the instantaneously? So don't think about those things. As I
Okay.
said, they're all intuitive ways. These are diagrams that you have, intuitive that you are drawing pictures to have an intuitive feeling.
Okay, sir.
That means the loop is some kind of fluctuations in the quantum field. I mean,
You can think, you can think in that, but these are not. See, these are some kind of see. You will have bubble diagrams also. So these are like fluctuations of the vacuum of the quantum field. But these loops are arising because of the interactions. For a free theory, you will not have any loop. For a free quantum field theory, there are no loops. There are only propagators, single lines, no loops for a free theories. The loops come into picture only because of the 5/4 interaction that you have put in.
okay, sir. Thank you.
Okay. Okay. Thank you very much. Let us stop here, and I
Okay.
would urge you to have some practice. Just go home and work these things out yourself, and you will. I can assure you that you will enjoy working these things out. You can play with other kind of theories also, for example, phi cube theory, and start writing down the possible Feynman diagrams, scattering of one particle, scattering of two particles. You can start writing diagrams and start deriving the Feynman rules in position space, in momentum space. For each theory, you will have a different set of Feynman rules and Feynman diagrams. So you can start playing with other theories. So this is one example of a theory, which is phi-4 theory, and practice with 5/4 theory, and then go to see other theories also. So let us stop here.